Okay, so let us see. So in CRE so far, we have learnt about the different reaction, kinetics and reaction rate. We also learned about, design of ideal reactors. Now, in reaction kinetics and rate, we learned about first order, second order, third order reactions, and the temperature dependency. So when we talk about temperature dependency, we talk about something like Arrhenius. So today I want to go through a newer topic, something known as a shifting order reaction. Okay, so let us take one case. Is Ra is equal to K1Ca square by K2 plus K3Ca. Okay, so let us say we have a reaction whose reaction rate is defined as K1Ca square by K2 plus K3Ca. Now there are two cases to this. Let's say case 1. Let's say the concentration Ca is very low. Okay, and case 2, the opposite, concentration Ca is very high. Okay, so in case 1, let's say the concentration of Ca is very low. That means K3Ca will be much lower than K2. Okay, so that means when we write the reaction rate by K2 plus K3Ca, we can neglect this term. Okay, and we can write this as K1 by K2. Let's say that we can take it as a constant into Ca square. So we can write this as, approximate this as K1 by K2 into Ca square. So this is basically second order. Okay. Now the case 2, there Ca, the concentration of A is very high. That means this K3Ca will be a lot more greater than K2. And when we write the reaction rate K1 Ca square by K2 plus K3Ca, since this K3Ca term is very high compared to K2, you can neglect this. So it will be K1Ca square by K3Ca. And this Ca will get cancelled here, and you can write this as K1 by K3 into Ca. Now the thing is, this is first order. Now like you get the gist of this shifting order. So depending on the concentration or depending on a variety of conditions, the reaction order can change. So in this case, depending on the concentration of the reactant, the reaction can either be a second order or a first order. So such kind of reactions are called shifting order reactions, right? Okay, so yeah, so that is about shifting order reactions. Now let us move on to a second order reaction. So we learned some basics of second order reaction. some peculiar cases of second order reaction. For example, A plus B gives product B, the reaction rate constant A. Okay. So if we write the rate equation for this, minus RA will be KCA CB, which is basically minus DCA by DT. Okay. And we saw how we can derive the final equation for this. So how we can do is, we can write minus dCA by dt is equal to k CA0 into 1 minus XA and CB0 into 1 minus XB. We can actually write this like this: k CA0 square. Okay, wait a minute. This is CB0 into M minus XB. Okay. So there is one error here. 1 second. Yeah. So this is minus dCA by dt is equal to k into CA0 into 1 minus XA into CA0 into CB0 by CA0 minus XB. But XB you can write it as XA. So basically what happens here is, so this is actually CB0 into 1 minus XB. Okay, and this XB you can write it as B by A XA. And here B and A are basically the coefficients of A and B. So this is A, this is B. So XB, and so since B and A are 1 and 1 here, XB will be equal to XA. And what we are doing basically here is just taking rearranging this in a way that we are taking out CA0 from this term. And other thing that we have to note here is this CB0 by CA0, or which is basically the ratio of the initial concentrations of the reactant. You can write this as M. Okay. So now if we rearrange this, dCA by dt is equal to k CA0 square into 1 minus XA into M minus XA. So this is the differential term for the reaction rate. Now all we have to do is integrate this. It's basically integrate by parts. And if you integrate this and finally you will get an equation ln M minus XA by M into 1 minus XA is equal to k CA0 into M minus 1 T. So this is the final equation after you integrate this by parts, and you will get an integration like this. So this is one thing, but what I wanted to mention here is that there are just like how we saw in the shifting order, there are a few cases here as well. So let's say case 1. I will write in a new page. So this is A plus B gives P, and minus RA is equal to K CA CB. Okay. Now case 1. Ca0 is equal to Cb0. So that means equimolar, reactants. So if you have 1 mole of A, so if you are feeding 1 mole of A and 1 mole of B initially to perform this reaction, this will be the case. So in the initial concentrations of both the reactants are same. So that means this M, which is basically, Cb0 by Ca0 will be 1. Okay. In such cases, we can approximate this reaction rate Kca into Cb as Kca square or Kcb square. Okay. So this is case 1. Now case 2, if Cb is very much greater than Ca. Okay, so in this reaction, what happens is the concentration of B is very much, greater than, A. That means, let's say this is, 1000 mole per meter cube. But this Ca, let's take it as, 1 mole per meter cube. Now, this, let's say we are having a change in concentration. So rate, minus Ra is equal to KCACB. So what I'm trying to say here is this rate, reaction rate will be affected by the change in concentration of the reactants. So let's say if the reactant, if the reactant concentrations are lower here, then the reaction rate will be also low. If they are high, then the reaction rate will also be high. But in a case like this, where one reactant has very high concentration compared to the other one, a change in the concentration of one of the reactants is, negligible. So let's say a reaction is happening and 10% of the reaction has occurred. So this 1000, so after some time, let's say the concentrations are like this. This will be, 990 and this is 0.9. Now if we look at the change between 1000 and 990 is minimal, but when we compare the change between 1 and 0.9, right? Oh, actually, yeah, okay, right. So here, how we can approximate this rate equation is this Ra is equal to K Ca into Cb. This can be approximated as, you can take this Cb as a constant. You can take the Cb as a constant and we can approximate this as K dash Ca. Okay. So this, for this case, this second order reaction becomes a first order. So such reactions, in such cases, you can call this as pseudo first order reaction. Okay. So these are the two cases I wanted to just mention with regards to a second order reaction A plus B giving products. And in case 1, when the products are when the reactants are equimolar in concentration, you can approximate it as a 2A gives product or 2B gives product kind of reaction, and the reaction rate will become like this, Kca square or Kcb square. And in the second case, where concentration of B is much greater than A, or let's say if the concentration of A is much greater than concentration of B, you can apply this concept where you can take the higher concentration term as a constant and you can approximate this as a first order reaction, and such reactions are called pseudo first order reaction. And let's say in the case of this concentration of A much greater than concentration of B, Ca, you can take it as a constant and you can write K dash into CB. This will be the rate. Understood? So any doubts regarding this shifting order reactions and pseudo first order reactions, please you can ask. Pseudo first order. Okay. So yeah, did you understand how we wrote this rate equation? Minus RA is equal to KCA into CB. Now, okay, I'll use the next page and do it. Okay. So A plus B gives P and minus RA is equal to KCA CB. Okay. Now let's take the case here where CB is much greater than CA. Okay. Let's take CB as 1000 and CA as we'll take it as 2 for our sake. Now if we calculate rate, let's take K as 1. Okay, just for concentration sake. So this rate will be KCA into CB. So that will be 1 into CA, that is 1000 into 2. So this will be 2000. Let the unit be whatever, that is fine. Now the same thing, let's say after a time t, this CB becomes 999 or something, and this CA okay, let this be 990, and this CA becomes something like, let's say 1.5. Now if we calculate minus RA is equal to 1 into 1.5 into 990. So can you guys calculate and let me know what is the answer here? 1 into 1.5 into 990. Okay, 1485. Okay, fine. Now let us get back into our question. Let's say we are now trying to accommodate for the change here. Right. Okay, let's say CB changed as 990, but CA didn't change that much. It still remained approximately 2. Now the rate equation will be what? 1 into 2 into 990. What is this? Something around 1980, I think. Right. Now what we are seeing here is, now we'll take the other case as well. But let's say CB, CA. Let CB be somewhere around thousands itself, but CA changed from 2 to let's say 1. Then the rate will be RA is equal to 1 into 1 into 1000. This will be 1000. So now you have 3 rate values. Okay, rate of reaction values. The first one, it is the normal condition. So you have 2000 is as the your exact rate of equation. Now in the second case, you approximated that the concentration of A remains constant, but the sorry, in the second case the concentration of B changed a little. Okay, so from 1000 to 990, the change is very small, that this rate value here is 1980. That is very, very much close to 2000. But in the last case, there was a variation in Ca, which was the lower concentration reactant, and we don't care about Cb. When the concentration of Ca changes, you can see how much the reaction rate also changes. So, how much the reaction rate also changes here. So you can see this is half of the original case. So that means the concentration of Ca has a bigger say in your reaction rate compared to Cb, because you just notice that even if Cb changes by little, the overall the value of the reaction rate does not vary that much, because the change is very little. But then if the Ca changes, even slightly, if it changes, there is a huge change in the value of your reaction rate. Okay, now imagine, let's say Cb is something like some 100,000, and Ca is something like 10 or something. Now imagine the change. If the Ca changes from 10 to 9, while the Cb changes from 100,000 to, let's say, 99,000, this Ca, the change in Ca will have more say in the reaction rate, which is given as minus Ra is equal to K Ca Cb. So this change in concentration of Ca will have more say in your reaction rate. So that is why you can approximate in this case this Cb as constant, because the change in Cb does not affect your Ca, right? The change in Cb does not affect your rate that much. So okay, to give you some exact values as well, let's take this same reaction. A plus B gives P, and you have 10 mole of A and 100,000 mole of 100,000 of B. Okay, so you just ignore this, that is fine. Now for every 1 mole of A reacted, so let's say 1 mole of A reacted with 1 mole of B to give you 1 mole of product at some small time, t is equal to 1 second or 2 seconds or something. Then after a time t, this A will be 9 moles. Okay, and this 100,000 will be what? 99,999 moles. Now tell me, which will have a more say in your reaction rate, which is given by minus Ra is equal to K Ca into Cb. At time t is equal to 0, this rate is equal to, let's take case 1 again. 1 into Ca, that is 10 into 100,000, and that will be what? 10 raised to 6 or 1 million as your rate units. Just some arbitrary values. Now the same case, if you take Ra is equal to, at time t, 9 into 999, you will get some value. Can someone just tell me what is the value? Okay, let it be some value, that is fine. Just calculate and let me know. Okay, fine. 899,991. Okay. Now the same case, you are assuming this pseudo order reaction, and you are just taking this 99,000 as 10,000 itself. I mean, sorry, 100,000 itself. Then 9 into 100,000 will be a reaction rate, which will be what? 900,000. You can see there is not a lot of difference between these two values. In the first case, you took the value of Cb and you calculated Ra. In the second case, as I approximated here, you took Cb as constant. You just took Cb as 100,000 itself, and you calculated the value, and the reaction rate is again very close to your original value. So this approximation is what we use and what we call as pseudo order reactions, and here it is pseudo first order reaction. So now did you understand why why we can approximate such second order reactions as pseudo first order reactions? So in this case, you can more or less write K is equal to K dash into just Ca, and this K dash will be what, 100,000 into K, and Ca will be your concentration of A, which is 9 here, and this is a first order reaction, and that is called as pseudo first order reaction. Now, like, did you understand why we are like able to take the concentration of Cb as a constant here, and we are able to approximate it, as a first order reaction? Okay. So yeah, yeah, we looked at shifting order reactions and pseudo order reactions. So I just wanted to like mention these two before we went on to solve some problems. So yeah, okay. Let's move on to problems then. Okay, fine. So yeah, just read this question, go through this question, and see what you can understand. We'll go through it. Okay. So fine. Let's see this question. So this is a question from GATE 2017 Chemical Engineering, question number 47. The following liquid phase second order reaction is carried out in an isothermal CSTR at steady state. A gives R with a reaction rate 0.05 Ca square mole per meter cube hour, where Ca is the concentration of the reactant in the CSTR. The reactor volume is 2 meter cube. The inlet flow rate is 0.5 meter cube per hour, and the inlet concentration of the reactant is 1000 mole per meter cube. The fractional conversion rounded to 2 decimal places dash. So this is a question based on design of ideal reactors, and the NPTEL reference lecture series can be found in module 1 lecture 17, design of mixed flow reactors, chemical reaction engineering 1, homogeneous reactors, by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So let us write down what the data that is being given here. So we have been given the reaction rate minus Ra is equal to 0.005 Ca square. We have been given the volume of the reactor V as 2 meter cube, and the inlet flow rate mu is given as 0.5 meter cube per hour. The initial concentration of the reactor is also given. So Ca0 is equal to 1000 mole per meter cube. We need to find the fractional conversion Xa. So all these is taking place in a CSTR. So this is a direct application of the design equation of CSTR. So we can directly start with our design equation for CSTR. So for CSTR, the design equation is tau is equal to V by nu, which is equal to Ca0 into Xa by minus Ra. Okay. So all we have to do is just substitute all these values for V, nu, Ca0, and RA, and RA you can write it as 0.005 into CA square. So let us start by substituting. V by nu is equal to CA0 into XA by 0.005 CA square. And we also know that we can write CA as CA0 into 1 minus XA. Now we'll substitute this into this CA and we'll get V by nu is equal to CA0 into XA by 0.005 CA0 square into 1 minus XA the whole square. So let us rewrite this. V by nu is equal to CA0 XA by 0.005 CA0 square into 1 minus XA the whole square. Once CA0 and CA0 will get cancelled, we will get XA by 1 minus XA the whole square into 1 by 0.005 CA0, which is equal to V by nu. So here we have the value for V, we have the value for nu, we have the value for CA0. All we have to do is just substitute these values and we'll get a quadratic equation in terms of XA. So let us start by substituting these values. So V, which is 2 by flow rate, which is 0.5, is equal to XA by 1 minus XA the whole square into 1 by 0.005 into CA0, and that is given as 1000. So this is, if we rearrange this and do the mathematical operations, we'll get XA by 1 minus XA the whole square is equal to 20. Now all we have to do is solve for this equation. So how we can solve, we'll see. So this is XA by 1 plus XA square minus 2XA is equal to 20, and if we rearrange this, we'll get 20XA square minus 41XA plus 20 is equal to 0. So this is our quadratic equation. Now all we have to do is just solve for this quadratic equation. And we can solve this as, XA is equal to 41 plus or minus root of 41 square minus 4 into 20 into 20 the whole by 2 into 20. So the solving method is, x is equal to minus b plus or minus root of b square minus 4ac by 2a. And if we solve this, we'll get two values. So one value will be above 1. So XA will be, one value will be greater than 1, and one value will be between 0 and 1. And this is the value that we can choose. So XA, if by solving this quadratic equation, and the quadratic equation is 20XA square minus 41XA plus 20 is equal to 0, we'll get XA as 0.8. So that means the fractional conversion is 80%. Now the right answer can vary anywhere between 0.79 to 0.81. Okay. So yeah, you can see like this is basically just a direct application question here. So what we did is we just directly applied the CSTR design equation. We just substituted for all the values and we converted this design equation in terms of um, XA or the conversion. So we'll get an equation like this: XA by 1 minus XA the whole square is equal to 20. Now all we have to do is just solve for this quadratic equation and we'll get one value which is a value that makes sense for conversion. So that the value that makes sense means it will lie between 0 and 1, and that value is zero point 0.8. Okay, is this clear? Okay, let's move on to the next question. Okay, so this question, we'll be using our pseudo first order case that we learned here. So just go through this question. Let's see how we can proceed. So this is a question from GATE 2017 from Chemical Engineering, question number 49. The gas phase reaction is carried out in a constant volume isothermal batch reactor. The reaction is A plus B gives R plus S. The reactants A and B as well as the product S are non-condensable gases. At the operating temperature, the saturation pressure of the product R is 40 kilopascal. Initially, the batch reactor contains equimolar amounts of A and B and no products at a total pressure of 100 kilopascal. The initial concentrations of the reactants are Ca0, Cb0 equal to 12.5 mole per meter cube. The rate of the reaction is given by minus Ra is equal to 0.08 CaCb mole per meter cube second. The time at which R just starts condensing rounded to one decimal place is dash seconds. So this is a question based on design of batch reactors, and the reference NPTEL lecture series can be found in Module 1, Lecture 10, Design of Batch Reactors, Chemical Reaction Engineering 1, Homogeneous Reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So let us see the details they have given us. So they have given that the reaction rate minus Ra is equal to 0.08 CaCb mole per meter cube second. They have also given that Ca0 is equal to Cb0 is equal to 12.5 moles mole per meter cube. Okay, so let us write down the reaction here. So we have A plus B gives R plus S. So at T is equal to 0, we'll have 12.5 moles of A, 12.5 moles of B, and the reaction that hasn't started happening yet. So the product will be 0. And let's say at time T, let's say X amount of A and X amount of B has reacted. So we'll have A as 12.5 minus X. So whatever is remaining after the reaction we'll have. So 12.5 minus X moles of A, 12.5 minus X moles of B. This will form X moles of R and X moles of S. Okay, so let us write this again here. So A plus B gives R plus S. At time t is equal to 0, we'll have 12.5 because this is Ca0, then Cb0 is 12.5, 0 moles of R and 0 moles of S. And at time t is equal to t, we'll have 12.5 minus x, 12.5 minus x of A and B, then x moles of R and x moles of S. Okay, so now at time t, the total moles will be the sum of all these four. So that is 12.5 minus x plus 12.5 minus x plus x plus x. So this is A, this is B, this is R and this is S. And all the x will get cancelled and your total moles will be 25 moles. Okay. Now they have asked us to find the time at which R starts condensing. And the other data that they have given is that when R is 40% of total composition, it will start condensing. So the condensing time, this T, will be when R is equal to 40% of total moles. Right? So when R reaches 40% of this total moles, we'll have our time T, which we need to calculate here. Fine. So, what we can do is, we have at time T, the moles of R is X. So, just mathematical calculation here, this moles of, I'll write, moles of R by total moles is equal to 40%. Right? So this moles of R is X and total moles is 25. This is 40%. That is 0.4. So now we can use this equation and find the concentration of X or the moles, number of moles, which is X, and that will give us the number of moles of R, S, and from that we can find the number of moles of A and B as well. So let us rewrite this. So X by 25 is equal to 0.4. That means X is equal to 10 moles. Right? So using this we can write, we just found that R is 10 moles. Then S is also X, which is 10 moles. Then A will be 12.5 minus X, that is 10 moles. And B is also 12.5 minus X. Sorry, this is not 10. Yeah. So A is 12.5 minus X. So that will be 12.5 minus 10, that is 2.5 moles. And B will also be 12.5 minus X, which will be 2.5 moles. Now what we can say here is, this is Cr, this is Cs, this is Ca at time t, and this is Cb at time t. Okay. Now, for a second order reaction in a batch condition, we have learned that the rate equation can be written as 1 by Ca minus 1 by Ca0 is equal to Kt. Okay, so this is the equation for a second order reaction. Now here the actual rate is minus Ra is equal to KCA into CB, because our reaction is A plus B gives R plus S. But since they have given that CA0 is equal to CB0 and the stoichiometry is also 1 for both the cases, we can approximate this rate as KCA square. And if this minus RA is equal to KCA square, then minus dCA by dt is equal to KCA square. And if we integrate this, we'll get this simple equation for second order reaction as 1 by Ca minus 1 by Ca0 is equal to KT. So using this equation, we can solve to find this time T. Okay. So let us okay. So now we have 1 by Ca minus 1 by Ca0 is equal to KT. We just found out Ca from the balance. We'll just substitute the values for Ca, Ca0 and K, and we'll find the time T. So Ca is 2.5, Ca0 is 12.5 and K is equal to 0.08, which is given in the reaction rate. Now substitute this. 1 by 2.5 is equal to minus 1 by 12.5 is equal to 0.08 into T. If we solve for this equation, we will get time T is equal to 4 seconds. So this is how we can proceed with this question. So basically what we did here is we wrote the balance of our equation A plus B gives R plus S. We just wrote the mole balance at time t equal to 0 and time t equal to t. And using these data, we can find the total moles, which is just the sum of these moles of individual reactants and products, which will be 25 moles at all times. So at t equal to 0 also it is 25 moles, and t equal to t it is 25 moles. This is because the stoichiometry here is 1 for all the reactants and products. So using this data, we can find the concentration of the individual reactant as well as the products. So what we did here is they mentioned that R will start condensing when it reaches total 40% of the total composition. So and also the time we need to calculate is basically when R starts condensing, or that is when R reaches 40% of the total composition. So we can write moles of R by total number of moles is equal to 40% or 0.4, and moles of R is basically just X and the total moles is 25. So X by 25 will be 0.4, and by solving this we will get X as 10 moles, or the concentration of R Cr is 10 moles. Similarly Cs will be 10, Ca will become 10, 12 minus 10, that is 2.5, and Cb will be 12.5 minus 10, that will be 2.5 again. Now the rate equation Ra is equal to Kca into Cb, and we just learned the cases for a reaction like this where there are two reactants in a second order reaction, and if the initial concentrations are same, then we can write or approximate this reaction rate minus Ra from KCACB to KCA square. Okay, so using that we are writing 1 by Ca minus 1 by Ca0 is equal to Kt as our reaction rate equation. Now all we have to do is just substitute all these values for Ca, Ca0 and K from our question, and we can find the value of T, which is our time required for this reaction to happen, and that will become 4 seconds. Clear? Okay, good. We'll look into one more question. So it's a question based on our pseudo shifting order reaction. So we just learned about the shifting order reaction, how a reaction the reaction order can change with respect to the concentration of the reactant. So this question is based on shifting order reactions. Just go through this question and we'll see how we can solve. Okay. So this is a question from GATE 2016 Chemical Engineering, question number 14. For a non-catalytic homogeneous reaction A gives B, the rate expression at 300 Kelvin is minus Ra is equal to 10 Ca by 1 plus 5 Ca, where Ca is the concentration of A in mole per meter cube. Theoretically, the upper limit for the magnitude of the reaction rate minus Ra in mole per meter cube per second rounded off to the first decimal place at 300 Kelvin is dash. So this is a question from reaction kinetics from chemical reaction engineering, and the reference NPTEL series can be found in week 4 lecture 1 integral method of analysis of batch reactor data, chemical reaction engineering 1 by Professor B. Mandal, Department of Chemical Engineering, IIT Guwahati. So here they have given that the reaction rate minus Ra is equal to 10 Ca by 1 plus 5 Ca. So this is a shifting order reaction. So that means there are two cases here. So case 1, when Ca is very high. So in case 1, since Ca is very high, the terms in the denominator 5 Ca will be very greater than 1. So we can neglect this 1. So the reaction rate will become minus Ra is equal to 10 Ca by 1 plus 5 Ca. This 1 gets neglected and that will be 10 Ca by 5 Ca, and this will be 2. So this is basically a zero order reaction. Now the case 2 is when Ca is very low. In that case, 5 Ca will be very less than 1, and the reaction rate will be 10 Ca by 1 plus 5 Ca, and since Ca is very small, we can neglect this 5 Ca term, and this reaction rate will be 10 Ca, and this will be first order. So depending on the concentration of the reactant, this reaction can have two orders, and such reactions are called shifting order reactions. So now let's get into the question. Minus Ra is equal to 10 Ca by 1 plus 5 Ca. Now they have asked us to find this Ra at theoretical upper limit. And when they say upper limit, it means Ca is maximum. or Ca is very very high, or that means 5 Ca is very very greater than 1. So this is the thing with case 1. So that means you can neglect this one term, and the rate equation will become minus Ra is equal to 10 Ca by 5 Ca, and this is basically 2. So this is the right answer here. So uh, I hope it's understandable. So I hope you guys are able to follow what we just did here. So when they mean upper limit, theoretical upper limit, that means it is the upper limit for the reaction rate or the upper limit for the concentration of reactant. And when concentration of reactant is very very high, you can approximate this into a first order into a zero order reaction, and your magnitude of the reaction rate will be 2, as shown here in the case 1. Is this clear? Okay. So today we looked into a few questions regarding shifting order reactions and pseudo order reactions. And in the next class, I wanted to go through a bit about series and parallel reactions. So let's see how we can go about that. And yeah, we'll stop here for today. And in the next class, as I said, we'll try to see series and parallel reactions, and we'll see how we can implement the reaction rates of series and parallel reactions in design equations for CSTR, PFR, and batch reactors. And yeah, we'll keep continuing solving a few more questions with regards to these concepts. So yeah, thank you for joining, and I'll see you guys next Monday.